Here we go. So today we are going to be still solving trigonometric equations, the same thing that we're doing. This is still section 5.3. It's just the most rigorous portion. So we've already learned how to solve it. We've learned how to factor and solve it. Now we've got some special cases. For example, if you can't factor it, what if it's not a factorable kind? How do you solve it? We're gonna do that today. These first ones, we're gonna try to solve it, but what ends up happening with these first few examples is we've got cases where you've got sines and cosines in the same equation. Those of you that have the computer open, it's gonna drain the battery. We don't need it open yet. Thank you. So this first one, we have sines and cosines in the same equation. We want to convert something over using those identities that we spent last week on. We want to use the identities to convert something so that we only have the same trigonometric function. So do I want to change sine x into cosine, or do I want to change cosine squared into sine x? Cosine squared, what is the identity I want to use? Do you remember it? Remember, cosine squared x is equal to 1 minus sine squared x. Remember that Pythagorean identity? Maybe you don't remember. Did you have a list of them? It might be helpful. Before I write any more, this is going to take up a lot of, it's going to take up a little bit of space, and I didn't leave you a lot of space, so warning. Very small. Sorry. All right. So all we did was substitute cosine squared x for 1 minus sine squared x. We just used what is equivalent to. We substituted. Now we're going to solve this. So what do I do that for? Distribute. We're going to have 9 minus 12 sine x equals 4 minus 4 sine squared x. Then we need to make this equal to 0 and factor it. So I'm going to move over the 4, move over the 4 sine squared x. So I set it equal to 0, and then we're going to factor it. If you have trouble factoring something that looks like this, you can always switch out the sine x for a different variable, like u. And you could make it look like 4u squared minus 12u plus 5. And think about factoring that first, if you need to do that. How do we factor 3 terms? Guess and check. 2 parentheses, guess and check. So we're going to have 2 parentheses. If I look at the plus 5, that tells me that both of the signs are going to be the same. If I look at the minus 12, that tells me that both of the signs are going to be what sign? Negative. So I know that. What can I multiply together to give me a plus 5? I only have a -1 and a -5. That's it. So now I just have to figure out if I'm using 4 and 1 or 2 and 2. So there's my guessing and my checking. It's 2 and 2. So I'm going to write 2 sine x and 2 sine x. And then from there we set each factor equal to 0. Sorry, like I said, there wasn't a lot of space on this one. We'll solve each one of these. So this gives me sine x as a half. And over here we have sine x is 5 halves. When I solve it. So we need to figure out at what angle is sine x equal to a half. 30 degrees, pi over 6. So also 5 pi over 6. And where is sine x equal to 5 halves? It's not equal to 5 halves, right? So that would be not possible. So we only have our two answers. Yes, Michael.
So the only new part of this is using these identities.
These, yes.
Okay.
We got 3 new parts today. 3 different things we're learning today. So yes. All right, another one? Try another one? Try. Okay, so I'm going to stop talking for a moment, and I would like you to, on your paper, see if you can figure out what you would switch out and solve it. I want you to try it. I'm going to pause the video. Okay, there were different attempts that I've seen. The way that I chose to do it was using that tangent squared x is equal to secant squared x. Is it it's minus 1, right? Yeah. And if you didn't put the parenthesis and distribute that 2 in, then it's not going to work. So 2 secant squared x minus 2 minus 3 secant x plus 3. And then I combine my like terms. So I get 2 secant squared x minus 3 secant x plus 1. So if we had that part wrong, obviously we're going to have factoring wrong and so on. I'm going to put 2 secant and a regular secant. That's how I'm going to get 2 secant squared. Both of them are going to be minus, and that's going to be 1 and 1. Let me factor it.
Yeah, no, I have that.
So then we're going to solve, set each of these equal to 0. So I get secant x equals a half. So that means that cosine x is equal to 2, but that's impossible. It can't be. That one's not useful. And we have secant x equals 1, which is cosine x flipped, still 1. So where's cosine equal to 1? That's 0.
It can't be 2 pi.
According to the directions, no. We just 0 through 2 pi, but not including 2 pi. So yes, 2 pi is true, but not according to the directions.
That's what I was thinking.
Okay. While I'm doing these examples, if I'm going too slow for you and you want to try stuff on your own and work ahead at your own pace, that's totally fine. Just make sure that you're doing them right when you look up here. The next one, cosecant x plus cotangent x equals 1. I'm going to show you how I did it. There are probably other ways, but I just want to show you my way so you have an idea of what you could try on your own. There's probably other ways of doing it. What I did first was I made 1 over sine x. Plus cosine x over sine x. This is going to get confusing, I feel like. Equals 1. All right. So then if we do it that way, we could cancel all of the denominators by multiplying both sides by sine x.
Don't you have to bring over the 1 first?
Huh?
Don't you have to bring over the 1 first?
I could. I'm just showing you things that you can try.
But you don't have to bring over the 1 first?
You don't have to first, no. So if I do it this way, I'm going to get 1 plus cosine x plus sine x. And what could we try? Is there anything that makes sine into cosine? There's not. So what I did next was I squared both sides. Why would I square both sides? So eventually this side's going to be 1 minus cosine squared x, okay? But if I square both sides, I can't just square individual terms. I have to write it twice and FOIL it. To write this twice. And then I have to FOIL it. And I did it really fast, so. Did it really fast. My like terms. Did the FOIL method. Okay, so at this point, I have all cosines. So now I'm going to try to solve it. I'm going to add cosine squared x to both sides, and I'm going to subtract 1 from both sides. And rearrange some stuff. What can we do to solve it? Factor out of 2 cosine x, and then you have cosine x plus 1. So we've got 2 cosine x equals 0, and cosine x plus 1 equals 0. Good luck.
1, so that was. 1 plus 2 cosine x.
I subtracted the 1.
Yeah.
Okay, so those cancel out.
Oh.
And I added the cosine squared x, which made 2 of them, and I just rearranged the order.
Okay, the order's good. Okay.
Yep, I thought that might lose somebody. Sorry. Okay, from here, if we solve the first one, 2 cosine x equals 0, same thing as cosine x equals 0. Where is cosine x equal to 0?
Wouldn't you have to divide by 2?
I did. Okay, and then over here, cosine x equals -1, so that would be at pi. All right, now I'm going to tell you right now, we've got a couple issues. Remember, sometimes you can solve things, but they aren't really solutions. They're called extraneous solutions. Do you remember that from a previous course at all, extraneous solutions? Some of you, yes, some of you no. So here's the thing that happened, is because we had squared it originally, we had put in, not originally, but when we did square it, we had put in extra x's that weren't there originally. So what ends up happening is the answers that we got were the answers to this step, but they weren't, they don't all work in this step here. What happens if I take my answers and I put in if I put in all my answers, not at the same time, if I put in one answer at a time, some of them don't actually work. How many have I put in pi over 2 here? Well, that one works. Shouldn't work though. What happens if I put in pi over 2 tangent over 2? I did it graphically. I'll show you it on the graph. But what happens if you plug them all in, sometimes we have extraneous solutions. And it's because we had to square it. It was the only one in our examples that's doing this. I'll show you the graph of this. Did I hit record? Okay. All right. So we go to Desmos, and you don't have to do this. I'm just going to do it real fast. You'll go to Desmos later. and we graph this function. What's the original function? Equals 1, so I'd have to do minus 1? Okay. So when we look, pi over 2 is the only solution. You see that? And it's because of the extraneous solutions. When I had plugged in other answers, some of them aren't going to work. Even though you got it as a solution, it's because we had squared it. That would be, if you do things to the equations like add in extra x's, this could potentially happen. So you just want to check it. And are you allowed to use Desmos to check your answers? Not on a quiz. But I'm not going to give you the hardest ones on the quiz anyway. So, but in your homework, check your answers on Desmos. Make sure you're doing them right. So only pi over 2 is that's the only one that works. So we have some extraneous solutions we can throw out, and it would just be the pi over 2. All right. Oops. The other two, I'm not going to do completely from start to finish and find all the angles. Let's just get to what you could switch out, and then it looks like yesterday's assignment, and not spend a whole lot of time on these. So if you look at this one, what could we switch out? Should we take out sine squared, or should we just take out cosine x? We're going to take out the sine squared because that one we have a Pythagorean identity for. So we would make this one 2 multiplied by 1 minus cosine squared x plus 3 cosine x minus 3. And then we distribute 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. And then we combine my terms. Negative 2 cosine squared x plus 3 cosine x minus 1 equals 0. I personally would do one more step before I factor. Do I have an idea? What do you mean by take out? You could factor it out, or it is an equation, so you could multiply both sides by -1 if you want. Either's fine. That too. You could also just add all the stuff to the other side. That would be another way of making that positive. It just changes all the signs. And then you could factor it and solve it, but we're not going to finish factoring and solving, okay? But you just do it the same way we've been doing it. All right, how about this one? What can we try first? All right, so we're going to do 2 sine x plus 1 over sine x. What was that? Sorry, it wasn't. Oh, find common denominators. Like this one here. I didn't do it this way, but we can explore it. That's what I did, but I'm going to explore this way. That's going to give us 2 sine squared x plus 1 over sine x. What would we do then? I'm going to go to what Evan had said earlier. You just multiply both sides by sine x. Multiply everything by sine x. can solve it. What would we do to solve it? By 2, right? We get sine squared x equals -1/2. What will we do? Square root. What happens if I square root though?
Not a real number.
And I got an imaginary number. So what would I do if I'm doing this on my homework and I'm like, I'm getting an imaginary number? What would I do? Open up your computer. Let's go to Desmos. This is what you do. You'd say, what is going on? Why am I getting an imaginary number? Let's graph it and find out. Yeah. So I'm getting an imaginary number, which I could keep solving it, but I'm getting an imaginary number, so I'm fearing that I'm not doing it right. So I'm going to go to Desmos, and I'm going to type in the equation. Let's see what the graph looks like. What are we looking for on the graph? The x-intercepts. So what's the equation? The original?
Yeah, plus.
Just making sure we're saying the original.
What?
Plus cosecant, is that what it is?
Yeah.
Does it equal anything to equal 0? Yeah. There are no x-intercepts.
No solution.
So the question is, where does that equal 0? But the answer is it doesn't. So there is no solution for that particular question. When you graphed it, it verifies the fact that there is no solution because there's no x-intercepts. So that could happen. Yes, Michael.
We need to track them before we do that.
Except you can't on a quiz or something. So I would rather you figure it out than go check it and see, okay, I've done my work right. It should be an imaginary answer because there is no solution. But I can't control what you do outside my room. So. All right, keep Desmos open. The next thing we're going to do is we are going to use Desmos to graph. It says to graph it, and there's a graph there, but we're going to use Desmos. If you'd like to copy anything down onto the paper, you can. We're going to use Desmos to graph these things. This is the next kind of different ones that you're going to see. What's wrong with that one?
There wasn't any.
Okay. When that happens, hand it to me because I can fix it usually, but go ahead and get a new one. All right, so go to Desmos, type in just cosine x. And let's fix our x-intercepts, or x-axis, I mean, by using this little wrench, the graph settings up here in the corner that I'm circling. Let's go to that and change our x-axis step to go up by pi divided by 2.
All right, whatever you just say, can you do that again?
I went to the wrench. My arrow is, or my little, what is this thing called? What's that little finger thing called? No, not the wrench. The thing that the arrow turns into. The cursor, that's really what it's still called. Okay. I don't know if they came up with a better name in the past 20 years. No. Okay. Anyway, my cursor is up here, the wrench, you there. And then we went to the X step. And I just typed in pi divided by 2. And when I did that, I have like pi's on my x-axis. You can use that wrench to do what I'm about to do, but I'm just going to use my fingers and zoom in so that it goes from like 0 to 2 pi. Ish.
Do I do anything after I click file? Everybody needs to check.
No, that's great. I'm glad you guys are being helpful because that's going to be way faster than me going to help if you guys help out each other. That's going to be way faster. Okay, so then the question is where are the x-intercepts? Boom. Remember, we can just click on them. You can just touch screen them. and it should come up as pi over 2 and 3 pi over 2. Those are the x-intercepts for cosine when nothing is done to it. So you're going to write on your notes pi over 2 and 3 pi over 2. If you want to graph it, you can, but we're now going to look at the graph, and I'm going to just do it as a second graph of cosine 2x. We have done this stuff before. It should be somewhat familiar. Cosine 2x. And then once you've done that, figure out where your x-intercepts are now. How many x-intercepts do we have now? We have 4 of them. We had 2, but because we put that 2 in there, it affected the period, and it took this spring shape, this accordion, and squished it together. It made a horizontal shrink. So we now have more of the graph in the same location. We have more of that graph. Double the amount of graphs. So now there's double the amount of x-intercepts. And if you look at the, I'll talk about that in a moment. Let's do the third one. Cosine half, let's do x. How many x-intercepts are there for cosine half x? There's just 1, where originally there was 2, but we stretched it out, now there's just only 1. So this blue one, let me turn off the x-intercepts so that they're not kind of in the way. This blue one, how many full cycles are in the window from 0 to 2 pi? How many full cycles from 0 to 2 pi on the blue one? There's 2 full cycles. Where could you get that 2 from the equation? Right. That's telling you like how many cycles there are. So what we did with this blue one is it was stretched out over 2 full cycles, and then we took that and we just went, we squished it in. Okay? You understand graphically what's happening between the green one and the blue one. Now what we're going to do is we're going to solve equations that have numbers in the spot next to the x. We haven't done that yet. So when we talk about solving equations, we're talking about finding the x-intercepts. So when I had a regular cosine, I had 2 x-intercepts. But when I had cosine 2x, I had how many x-intercepts? 4 of them. It doubled it. And we could even try this real fast. Make another one, do cosine 3x. Do cosine 3x. And see how many x-intercepts there are. Six. Because it was originally 2, and now there's 3 times as many. So guess how many x-intercepts there would be if I did cosine 10x. You don't have to type it in. You should be able to follow this pattern. How many would there be if I had cosine 10x? Oops. Yeah, there is, because we took 10 full cycles and squished it in between 0 and 2 pi. So now you're not going to be doing this graphically. You're going to be doing this algebraically. You know what? Math is everywhere. All right. So this very first example is nothing new. This is what we've been doing. What are the answers for the cosine x equals a half? Where is cosine equal to a half? Okay. So that just has two answers because the 1 is in front of the x. We're going to pause on the Desmos for a moment. We'll look at it in a little bit, but you gotta learn how to do this graphically. Algebraically. Otherwise, I'm not going to be able to use this. Okay, so is this the next one, or is that's not the next one? That's not our work. Hold on. I switched the order. I didn't switch my slides. I did this one next. Okay. First thing you want to do is just solve it normally. Just solve it like it was sine x, not sine 2x. Just solve it normally. Let's figure out what it would normally look like. Okay, it's not sine x equals 1, it's sine 2x equals 1. So we're just going to pretend that sine x equals 1. What would the x values be at sine x equals 1? Or what angles? At just pi over 2. At just pi over 2, right? At just pi over 2, right? So that's the original, but it's not. It's not sine x, it's sine 2x. What I want to say is, because it is sine 2x, that means there's 2 full cycles that got squished into 1, 0 to 2 pi. So we have this pi over 2, but then we add on another full cycle and find a second x-intercept 1 more full cycle later. Because we have 2 full cycles that got squished into 0 to 2 pi. So we're going to find that second x-intercept before it got squished. So all you do is take this pi over 2 and add 2 pi onto it. How do I add 2 pi onto that? It is. How did you made this into 4 pi over 2? Right? And then we added those. That looks like a time. We're going to add those. And so our second x-intercept would be 5 pi over 2? Yeah, 5 pi over 2. Okay. That is if it wasn't squished. That would just be 2 x-intercepts in a row. But it got squished in. So because it got squished in, we have to divide originals by 2, or times by half. So if you take both of those and you divide by 2, or you multiply by half, we get pi over 4 and 5 pi over 4. Yes? Okay. There are 2 full cycles when this is a 2. There's 2 full cycles. Right? We saw that on the graph. There were going to be 2 full cycles in that same space. If I just graph sine x equals 1, that's only 1 cycle. So if I graph sine x equals 1 twice, if I graph sine x twice, that's going to give me my 2 full cycles, right? But to get the second one, it's a full 2 pi. So every cycle that we're adding on, you always add 2 pi. This is what you're going to do every time.
So it's just like pi half, like position wise, is the same as like 5 pi.
is the exact same position, right? It's just 2 pi later. So if you think in unit circle, and you go all the way to pi over 2, and you add 2 pi onto that, you're back at that same spot. Or you add 2 pi onto it, you're back at that same spot, and so on. It's coterminal angles. Okay, this, by the way, is our answer. We are done. We could check it. You don't need to check it right now. I'll just show you, and then we can check the next one on your own. But to check sine 2x minus 1, we just go to Desmos, turn off these, and we would do sine 2x and then minus 1. And then we look between 0 and 2 pi, and we have pi over 4, and we got 5 pi over 4. So we've done it correctly. All right, let's try another one so you can see the procedure again. So we're going to look at our original. Our original x-intercepts. We're going to be looking at where is cosine x equal to a half, which we've already done. Where is cosine x equal to a half? The original. At pi over 3 and at 5 pi over 3. Oops, I didn't write that, did I? Huh? Nah, maybe. It's a lot of material, I know. Okay, so we got 5 pi over 3, or 3 pi over 3 and 5 pi over 3. That's where it originally is. How many cycles are we doing? We're going to do 3 cycles. So that 3, that's how many cycles. So how many times should I add 2 pi? 2 times, because here's the first one. So I'm going to add 2 pi and then add 2 pi again. And I'm going to list all of those answers. But when I add 2 pi, this is a pi over 3, so I'm really adding 6 pi over 3. So it's common denominator. So if I add 6 pi over 3 plus pi over 3, I get 7 pi over 3. 6 pi over 3 plus 5 pi over 3, it's 11 pi over 3. And then I'm going to add another pi over 2 pi. Another 2 pi, because we're going to add another rotation on, another cycle. So for here, I got 6 pi plus 7 pi over 3, so 13 pi over 3. And then 17 pi over 3. So those would be my originals. That would be 3 full cycles. But then we have to do the part where you squish it in. And to squish it in, you have to divide by 3 or multiply by a third. We have to now divide by that number or multiply by that number. And these answers should be in order. If you've organized them and listed them the way I've done it, they should be in order. So we do pi over 3 multiplied by a third. So do we get pi over 9? 5 pi over 9, 7 pi over 9, 11 pi over 9. Oops, that looks like a G. There we go. 13 pi over 9, and 17 pi over 9. Nope, all of them. Because we're squishing all of them in. You take the originals, 3 full cycles of the original, and we squish them all in. Okay, let's do it one more time so we've got the pattern down of what you're doing each time. What's wrong? So we added 2 pi onto those, and then we added another 2 pi on from the last number. So 6 pi over 3 is 2 pi. So 7 pi plus 6 pi is 13 pi. Yes,
So
ma'am.
most of the time, will it only be pi over 3, pi over 6, and pi over 4? Just so
Pi over 2.
yeah, pi over 2.
I mean, it's only gonna be the unit circle stuff.
Yeah, but it would be always those starting, or is there something?
If this was like cosine x equals negative a half,
Yes.
then it wouldn't start at pi over 3. So not necessarily. It just depends what is given to you to start. Let's do one more for good measure. Ready? Cotangent squared 3x equals 3. So we see the 3x there. We're going to ignore the 3x for a moment. We're just going to find the originals. Like cotangent squared x equals 3. We're just going to find that to start. Then we'll take care of the 3. The triple in there. How do I solve that? Square root, so we're going to have cotangent x equals plus minus square root 3. Now what do we do? Change it to tangent, okay? So that equals plus minus square root of 3 over 3. So do we know where tangent is plus minus square root of 3 over 3? What's the first one? Pi over 6. Then 5 pi over 6. 7 pi over 6. And 11 pi over 6. Well, those are the starting ones. How many cycles are there? There's 3. That's our first cycle. Our second cycle is going to add 2 pi. Our third cycle is going to add another 2 pi. But I got to add 2 pi with a denominator of 6. So what is that? It'll be 12 pi over 6. I move it over. I don't leave myself enough room. Okay, so when we add 12 pi over 6 plus 1 pi over 6, we get 13 pi over 6. Then we add 12 plus 5, we get 17 pi over 6. Then we add 12 plus 7, we get 19 pi over 6. We add 12 plus 11, we get 23 pi over 6. Then I'm going to do my third cycle. I'm going to add 12 plus 13 and get 25 pi over 6. And then 29 pi over 6, right? And then 31 pi over 6. And 35 pi over 6. Those are the originals. Oh my gosh, we're not done yet though. What is our final answer? What do we do to the originals? We multiply everything by 1/3 or we divide everything by 3. So what will the denominator be for every single one of these? It will be 18, but none of the numerators change. Okay? Couldn't you have done that earlier? Maybe. Or you can rewrite them all. These are already in order. Once you, if you got that copy down, once you graph it and see it. Graph it and see it, that we should have 12 exponents. Because there were originally 4, we got 3 times that amount, 12 of them. How are we going to do it? Cotangent squared 3x. And then how do you make it equal 0? Minus 3. So between 0 and 2 pi, we have 1, 2, and look, it's all the numbers that I just listed when you're clicking on it. But it's not 1 day, it's 2 days. That's the unfortunate part about the log there. All right, we're almost done. Promise, we only have 2 examples left. That's all we got left, 2 examples. 2 examples. All right, how are we going to solve tangent squared x plus 4x plus 2?
Wait, is it calculator or quadratic formula?
Did I say?
You wrote using the correct quadratic formula. It says calculator.
Oh, that's wrong. The notes that I had originally had us doing it on the calculator and then using a quadratic formula, and I said, nope, we're only going to do quadratic formula. So we're doing it. That was terrible. Quadratic formula. Okay, why would we be doing quadratic formula? Because it doesn't factor. It doesn't factor. So we have to use quadratic formula because it doesn't factor. That's okay, you guys know this quadratic formula, right? All right, let's sing it. Ready? Oh, yeah.
Singing it.
X equals opposite b plus or minus square root b squared minus 4ac all over 2a. If you don't know the quadratic formula, you have to know it. It's a requirement for math skills. You gotta know it. If you don't know it and then you're using it wrong, you're gonna get it wrong. I'll see it later. All right, so we're gonna use the quadratic formula, and you're gonna use it just using your coefficients, a, b, and c. But when we do this, we're not actually solving for x. We're just solving for tangent x. You're solving for tangent x when you do the quadratic formula. So we're going to do opposite of b, so minus 4, plus or minus square root b squared, which is 16, minus 4 times 1 times 2, all over 2 times 1. Then you simplify everything, and you get negative 4 plus or minus square root 8 over 2. Then you simplify things further, and you get negative 2 plus or minus radical 2. I went really fast on that simplifying. But it doesn't actually even matter if you simplify it, so I'm not going to go over that right now. You just get what the tangent of x equals. So you use quadratic formula, you're going to get the tangent of x equals something. But I need to find what? What's x? It's what? We need to do that, but what is x? X are the angles, yeah. We need to find the angles. And to do that, we need to do inverse tangent. So this is what we should be thinking about. Okay? That's not on the unit circle, so we are going to use our calculator to do inverse tangent. Everything that we're doing right now is a repeat of things that you've done already this year. As of right now, this is all a repeat of stuff we've done this year. So you're going to find where the angle is equal to, and you can't type in plus and minus, you've got to do them separate. So you're going to find just one of them. Let's start with second tangent. Negative 2 plus square root 2. Let's type that one in. We'll just do the plus to start. Second tangent. get approximately, what'd you get? I mean, this is like more decimals, but you got approximately negative 0.5299. All right, I'm going to come back and do the negative in a second. I'm going to come back and do the minus in a second. I'm just going to go with the plus one. Where is radians? Where is this located? Sorry, I meant to say that earlier. Thank you for reminding me. You have to be in radians because we're doing radians. Okay, where is this located on the unit circle? Negative angle about here-ish. But the directions say our answers need to be between 0 and 2 pi. So can I put down a negative answer? So I have to find the positive version of that negative 0.5299. So what I need to do is I need to add on a whole 360 degrees. I need to add on a whole 2 pi to get to the other side. So on your calculator, this was the answer I had, and then I just hit plus 2 pi. So that's really at 5.75328, something, whatever numbers. So approximately 5.75-ish. What did I say it was? 5.75. Okay. So that's one of the answers. However, there's another place that tangent is negative besides fourth quadrant. It's also over here. So how do I find that angle? It's the same as this one, same reference angle. How do I find this one? So to get this one, we added 2 pi. What did you say to do? If I take this number and I just add pi, if I take that number and I add pi, I went the wrong way though. If I add pi, that will get me to that spot. Or if I took pi and I subtracted this number, that would also get me to the same place. So on my calculator, if I have this number and I add pi, 2.612-ish, 2.612. Do you remember doing this in chapter 4? A while ago. Remember, we had to find 2 answers from a radian. It was a while ago. So we're doing it again. All right, but that's only negative 2 plus square root 2. We still have to do it for negative 2 minus square root 2. So we're going to do it again. We're going to do second tangent. And we're going to do negative 2 minus square root 2. So we're going to do the whole process again. So you type that in your calculator, and what'd you get? Approximately negative 1.286-ish, 58. So that is negative. It's going to be in this quadrant. But I can't use that one, so what do I do to get the other one? Let's add 2 pi to it. Do it in a different color. Add 2 pi. It'll go me all the way around. So my calculator just plus 2 pi. 4.997. Is that what it was? Did I do it right? Did you do it too? 4.997. Where else is there another answer? Which quadrant? Second quadrant. For tangent, it would be. If it were cosine, it'd be a different quadrant. Second quadrant for tangent. To get that, we could take pi minus 1.286, or we could take pi plus the answer. So that's what I'm going to do. And I got 1.856. So we have 4 answers. What's the first one? First one is 1.856, then 2.612, 4.997, and 5.75. I didn't really round to the same thing each time, sorry. It's all an approximation. How could we check our answer if we were unsure? We could go to Desmos, and you could click on the x-intercepts, and they will be numbers like that, because it doesn't have a pi. And it will be answers like that.
So we don't have to do
No, because not on the unit circle, you won't be able to.
You
All right.
can also plug it back in.
You could plug it back in, yeah. Okay, I'm going to stop so that you can actually try these on your own. And I did work out the last one. It will be on the notes if you just pull up the notes if you want to see the last one worked out, if you want to see another example when you do your homework. I have done it, but I want you to have some class time to actually try it. Okay? So if you feel like the least confident with this part, because we only did one example, maybe start with that part and ask questions. All right? And then you can go on Canvas and check out the video.